Good day. This is Brian R. Smith, and let me take you through Tic-Tac-Toe Blitz, where a draw is for losers. First, let me get some of the plumbing out of the way. Got the credits. Here I am, and it's November 19th. And let me show you some of the activities. I've got 3 different activities that I use to run this game. There's the menu activity, which is these set of buttons and a difficulty toggle. Every time you click on that toggle button, this will go from easy to medium to hard level of difficulty, and then back to easy again. And of course, you just saw the credits button there. And then once you start a game, you go to the main activity, where it's just a surface. I do all the drawing of the game there, and then I give any player the ability to say, I give up. If you click on that, then you'll be taken to the activity over game, where I'll give you statistics about who won the game. And you can click on the play again, and they'll bring you back to the menu activity. So let's play this for human versus human. So this plays a normal game of tic-tac-toe. X goes first, then O, and here X is going to try to trap, or O is playing into X's trap, and so X will play here, and then O's got to defend, but then X is going to win, so player X wins outright. And we'll play again. And this time we'll play to a draw, so we got the same kind of start, but now O is a little bit smarter, and really now we just kind of play around the wheel, and we get to a draw. But you notice here, player O wins the draw. So in Tic-Tac-Toe Blitz, where a draw is for losers, there is no ties with that. So it's the player who plays the quickest. In this case, player O played the quickest in terms of the number of seconds per move, actually wins the game. So you want to go really quick. And my wife and I played this, and we had a lot of fun with it last night, because if you go really quick, you can make a mistake, and the other player can win outright, even though we all know how to play a game of tic-tac-toe. But if you're going quick, you make mistakes, and especially against a computer, and it makes for a very interesting game. So that's the human versus human. Let me take you through a little bit of the code that kind of supports that. Basically, for the game type, I go into a case where it's both the player versus player and the player versus computer, and I'll explain that a little bit later. Keep track of some information about the blitz statistics that I'm capturing, including like the start times, so I can keep track of the amount of time it takes the player or the computer to do its move. And then if it's a valid move, I play the sound effects for the swoosh sound, which is a good sound, and make the players move. I invalidate to cause the screen to be refreshed, when the computer has the opportunity to do that. Keep track of the game state, and then move on to the next player mechanically inside the program. And then I test to see if this is the end of the game. If the game state is end of the game, in other words, it's a draw, or a win, or a win by X or a win by O. And then if it is, then I'm going to start the intent over activity, and by sending this extra information over to there. And if it's not the end of the game, then I check. I've got a special case here where if it is a computer that the human is playing against, then I do run a computer turn. And then the other case, this is the else, where it was not a valid move by the player, so it'll be playing an error sound. So if I go into here, human versus human, if I click on a cell that's already been selected, I don't know if you can hear that, but there's like a bonk, bonk, bonk kind of sound. Or if you click outside of the hash area, you get that same kind of sound. Okay, and so that's the player versus player. So let me take you through the player versus computer. The difficulty we're going to do is an easy level of difficulty. And for this, it's just a random cell that the computer is going to pick. The player always goes first, and the computer just randomly picks, doesn't even try to defend, and randomly picks and allows the X to win just outright. So let me show you a little bit about that code. So down here, I've got a big case statement for the make the computer move, and this is the game difficulty of easy. And this logic is pretty simple. What I do is I find all the empty cells, and then I randomize one of those empty cells, and I pick that one, and the computer makes its move. So it's pretty easy, pretty simple logic, and definitely easy to beat. Let me take a look at the hard level. So now I'm going to toggle over to hard, computer versus computer. Of course, this is using the mini-max. So here now the computer's going to be playing a more aggressive kind of game. I'm going to try to trap the computer, but it's not going to fall for it. And so what we do is we end up going around the wheel, and we have our draw because we're both smart players. But you notice here, because this is Tic-Tac-Toe Blitz, where a draw is for the losers, the computer, player O, actually wins the game because it was faster per move. So I take a look at the number of seconds per move. It was faster, so you've actually got to go quickly in order to beat the computer. And again, it makes it for a much more interesting and fun game. So let's take a look at the Minimax algorithm that we're using here. So skipping over the medium difficulty, which, by the way, was a little bit harder to create in terms of the number of lines of code. Here we enter the hard. And what I do with this is, instead of calling Minimax right away, I actually loop through the entire hash, and I find then all the empty cells. And then I then I make the move. This is going to be the move that the computer is going to be making. And then the first call into Minimax is maximizing false. So I'm actually doing it for the other player. And the reason I did this is if I keep this loop out here, then I'm able to know what the column and row move is, so I can extract that information when I get the answer about which one of those cells, those first choice cells from the computer, which one of those Minimax will return as the best cell. So by separating kind of that logic out, that allowed me then to call Minimax once from inside of here for each one of those empty cells. And then Minimax will run down to the end of all the choices, and of course fold everything back up recursively, and then I'll get the best answer here, and then I can take advantage of that. So that's what I do for the first part of the Minimax. And then this is the actual Minimax algorithm here. So this is pretty standard. If the game state is at end of game, in other words, I've gotten all the way down to a leaf where there's it's either a draw or an X win or O win, I then score that with my heuristic, and then I return that information. And otherwise then, if in Minimax, if this is the computer player, I will find all the empty cells at this level. I will make the move. I will then call Minimax saying, well, it's the other guy who's playing, so is maximizing as false. I then unmake the move when I come back from Minimax, and then I keep track of the best score. And I do just the opposite, similar kind of logic, but just the opposite for the human player. It's just that when we're calling here now, the other next player is going to be the computer, so we want to do the is maximizing is true. Otherwise, it's similar kind of logic. And when I'm done with each one of these, I return the best score, which of course gets folded back up. So that's the hard level. And then I've got the computer versus computer just to check the algorithm. And of course, in here, what I do is just every time you click, the computer will run and play itself, and will just always go into a draw. And it just depends upon how fast you click on those, whether it's going to be the X player computer or the O player computer that wins, based upon the amount of time it took for the human to actually click on the buttons. So that's some of the basic mechanics and plumbing that's in the Tic-Tac-Toe Blitz. Let me take a look at some of the modifications. I showed you the sound a little bit, but there's over here there's the arrow select sound and the swoosh sound, and the sound is pretty simple. Basically on the on touch right at the beginning of it. So as soon as the player touches, it's either going to be a valid click or an invalid on touch, and so I will stop the sounds from playing, and then pretty soon into where I know it's a valid move that's been chosen by the user, I will play the sounds for a swoosh sound, which is a good sound, else I will play the bonk kind of sound for an error sound. So sounds pretty simple to add into Android games. I did reskin the X's and O's instead of drawing them myself. So I've got the hash that I just draw as just an image. I've got the O's and I've got the X's. So I just draw those onto the screen. So that's pretty simple there, but it's kind of a reskinning. Then I did do a medium difficulty. And for this, what I did is I used a greedy algorithm with a little extra logic to it. So basically, the computer will always try to pick one of the corners or the center. And so that's its greedy algorithm. But what it'll do, it will look to see if it needs to block the other player, and it will look to see if it has an opportunity to win the game. So let me show you some of that logic for the medium level. It's actually turned out to be a little bit complex to write, or at least more lines of code. So here's the medium. Keep track of some information here about whose turn it is. And then I look to block that easy win. I look to block or for a quick win for the computer. And then what I do is I find all the empty cells that are there, and I keep track of two different types of empty cells. One is the greedy cells, which are the corners and the center, and the other are just all this rest of the cells in case all the greedy cells are already chosen. So then the next thing I look at is are there any greedy cells left, and if there aren't, then I just grab whatever cell is left. So a lot of lines of code. Logic is not that complex, but it plays a pretty good game You can trap the computer, trick it into making moves, but it doesn't make any dumb moves. So that's the medium level modification I made. You saw the Tic-Tac-Toe Blitz, right, which is draws for loser. And basically for that, in terms of logic, it's pretty simple because I'm just keeping track of the timer events. So as I'm making the moves, right, I keep track of when the time started. I keep track of the number of moves that I need internally to know when I'm done with my blitz. And then right when the game is done, so it's inside of the logic that's in here, then I just keep track of how long it took, the elapsed time, and add those up, divide by the number of moves. That's why I need to know how many X moves there have been, how many Y moves, because in a game, X gets one more. If a game goes all the way to the draw or to the last play, X always gets one more move than O, so I need to know the maximum number, or the number of times that X moves versus O, so that I can get the math in terms of the seconds per move. So pretty simple, but I like what it does to the game in terms of really spicing up the fairly boring old tic-tac-toe, now that we're all playing tic-tac-toe blitz, where a draw is for losers. And then the other is what I do is, because the computer, just the minimax or any of the algorithms, the computer will always pick the same way of playing the same time. And as a human player, you can be ready for that. And so what I do is I randomize up, like even in minimax, I randomize up if there are equal best choices. Then right here, I will randomize up and I will pick one of the other equally best choices, so that if you're expecting the computer to always play in this corner on the first move or its first move, well, it will pick one of the other corners because they're just equally good. And so that random placement of equally good moves by the computer throws off the human, makes them think a little bit before clicking, moving the mouse or clicking with their finger, the on-touch event, and so that will slow down the human a little bit, and again, makes the game really good. So that's just one of the other modifications. And then what I really learned in terms of my personal reflections about this, the asynchronous task. I never have done that before, so I was able to take a look at the code and basically kind of copy it and make it work for my environment. And so it's basically the same kind of logic where the computer is making the move. I'm calculating, here's the start times, and I'm calculating, doing the delays so that the computer's got the delays, so it's not just an instantaneous selection. Keep track of all my blitz information, and then check to see on post execution if we're done with the game, and then I'll do the intent to get over to the game over activity. But yeah, it was an interesting exercise. It worked the first time for me, but it's really, I had to learn that, so that was part of my reflections. Then the other is passing the data with intent. So I hadn't really played with a lot of different activities, and that was another thing that I had to read up on. But in the end, this was fairly easy to pass information from one activity to another activity and to actually get over to that other activity. So that was something that I thought was going to be difficult, but really turned out to be, once you read up on it, turned out to be fairly simple. The minimax algorithm, I have to admit, I spent, you can see here, I spent a whole lot of time. This is version 2 of the Minimax, and I had a version 1 of the Minimax, and I had other bits and pieces. So I tried the Minimax in a variety of different ways, and so it took me a while to actually get it working. I have to admit, I hadn't done recursive programming probably since the 1980s, and so it took me a little while to get back into that mind frame, but once I got it, it works great. So thank you very much, and have a great day.